Welcome everybody, it's Rev. So this is a follow-up to my video that I released about a month ago, which was titled Game Theory War League Win Rate Denominator Matters. And what I basically stated in that video was that two teams could have an identical win rate. In this case, we're going to empirically prove this with math, of 60%, but or an expected win rate of 60%. Um, but given the War League structure is you need to win at least 3 out of 5 matches per week. If you had two teams, a streaky team and a non-streaky team, the less streaky team, given a positive win rate, would have a higher War win rate at the end of the season. And a lot of you came at me. You said, "Oh, that's bullshit. Uh, you need to prove this." So I'm going to prove it. It's a mathematical, statistical certainty. It's a fact. So I'm going to go over it. The only argument after this video is going to be whether or not you believe that certain teams or decks are streakier than others, which I think is almost certainly the case. I mean, if you even look at like several hundred game samples of Warrior data, it's way streakier. It has a way higher standard deviation of its win rates than Chaos Turbo. It's a streakier deck. You get shitty ass noobs going on insane tears with it, and then they can't win for like 14 games straight. That's just the deck. It's a streakier deck. It has more variance. If you're gonna argue over that, I mean, I just don't think you're paying attention to the format. Chaos Turbo is more consistent, and I think is overall less streaky. And I think that's a big reason why all Chaos Turbo teams, like Bugs or like Solly, did well despite not necessarily having the highest match win rate. We had a lower variance of win rate. So I'm going to prove that. So let's get into this. I'm not going to get super into the weeds. I'm just going to explain some mathematical notation because this was a requested video and I've been putting it off just because I frankly didn't feel like doing this. So evenly distributed wins. So we're going to build a model that models a few things. So we're going to use the base case, which is more or less a win rate model, which does not account for variance, and then one that does account for variance in win rate. And then how different that looks when you incorporate a non-streaky or a streaky team. So here's the model. You've seen this if you've watched some of my vids before. The probability is given the binomial formula, which we basically use as this. So as I had mentioned, the probability of a individual player or match winning on any given week is 60% or 0.6. The mathematical notation here is K is the number of wins, and this is basically just modeling out the probability of winning an overall week. So not any individual match, but a week, because you have 5 players and you need to win at least 3. So the probability of winning a week is going to be this formula here. Sigma is summing k equals 3, but again, you can win a week multiple ways. So we have to model it multiple ways. We can either win 3 out of 5 matches, we can win 4 out of 5 matches, or 5 out of 5 matches with a sweep. So we have to sum all of those probabilities together here. So we're going to take 0.6, our win rate, times basically to the third power, times 0.4, which is our loss rate, sum up, or I guess not sum up, but multiply all those numbers, and then we're going to do it again for 4, then we're going to do it again for 5. Now, when we sum all these numbers, what do we get? Probability of winning any given week, given that your team or your individual players each have a 60% win rate, means that your team has a 68% win rate to win on any given week. And this is something I covered in a separate video, but if you have a positive win rate with individual players, your weak win rate is actually higher. The exact opposite is true with negative win rates. So again, if every player had an exactly 60% win rate, your expected win rate given no variance would be 68%. No variance. Now we're going to model this with streaky wins. So we have to add basically one more variable in here. So we need to model the streakiness. Wrote this out kind of as a reminder to myself. and the probability given 0.5 that a team is hot is 0.8. That's basically, they have an 80% chance to win, and with a probability of 0.5, they have a 40% chance of basically winning if they're cold. So this can kind of be confusing. If we basically take 50% of 80%, that's 40%. If we take 50% of 40%, that's 20%. So if you add the 40% plus 20%, you still get an expected win rate of 60%. But we have to add basically a 50% probability that the team is running hot and has an 80% win rate, and then a 50% probability that the team is running cold and has a 40% win rate. But again, this down here just basically is showing that the team still overall, each individual player has an expected win rate of 60%. It's just sometimes they're running at 80%, they're running hot. Sometimes they're running at 40%. Sometimes they're running cold an equal amount of times. So this is basically the new formula. Should look very familiar. Sigma is sum, 5K. K is the number of wins. 80%, so that's your win rate. K is again going to be the number of wins, and then your loss rate is of course going to be 5 minus K because there can't be more than 5 matches. So if there were 3 wins on any given week, K would be 3. 5 minus 3 is 2, which is the remaining 2 matches at 20%. So that is going to be the first part of our formula. It's basically going to be the exact same for 40%. So again, you sum it up for 3 wins, 4 wins, 5 wins. That gives your overall win probability. If you're running hot at 80%, your team's win rate is going to be 94%, about 94.2%. But let's look what happens when you're running cold. So assuming you're running cold, we're going to do the exact same calculations, and I'll maybe scroll a little bit slow if you want to check the math or whatever, or plug in different numbers. But we're basically taking 3 wins, 4 wins, 5 wins, adding them all together. And that means if you're running cold and a given player or team is only having a 40% win rate, your expected win rate for the week is about 32%, 31.7. So what we need to do now is weight those equally because we're assuming that there's an equal probability you're running hot or you're running cold. So we're going to take 0.5 times 94%, 0.5 times 0.31% and add those together. Now let's do that. So 0.5 times that number, the 94%, 0.5 times this number, the 31-ish to 2%, that's going to sum out to 63% roughly if we round it. So that means a streakier team, given, again, the exact same win rate of 60%, but given more streakiness, is going to be expected to win 63% of their weeks. So that's a pretty big difference. And I kind of wrote up the conclusion here. So that means if both teams average 60% win rate per match, the evenly distributed team, that meaning a team that basically, um, you know, doesn't like go on like 5 game win streaks or 5 match loss streaks, but kind of has the more evenly distributed like win loss, like that kind of thing, as opposed to win loss, that being evenly distributed. They're expected to win 68.26% of the time of the weeks, while the streaky team is expected to win 63% of the time. The difference comes from the fact that the streakiness increases variance, and the streaky team's cold weeks, they perform significantly worse. And even though the hot weeks are very successful, the overall effect is a lower probability of meeting the weekly win threshold. This is a mathematical proof. Yada, yada, yada. So that's basically it. And if you're wondering if the same is true for teams that have, let's just say, an expected 40% win rate, it's actually not. It's actually better for shitty teams to be streakier. They actually have a higher probability of winning a week if they start at 40% and then add more variance. It's why bad players typically like high variance decks like Jeri Gumo or RGT or whatever it might be. It's because they're shit and they need to rely on variance to get them closer to 50%. So it's kind of funny, like in the opposite scenario, if you flip it on its head, If you're a positive, good win rate team or player, you want to reduce variance as much as possible. If the inverse is true, you want to incorporate variance as much as possible. This is something I've talked about, and I mean, I've pounded the table on it for like months. Like, but like in Edison, like bad players should just run Lightsworn. Like, it's literally one of the best decks. Nobody even knows it except like I feel like me, like and a few other people that have like seen the light, pun intended. But like it's a really good deck, and if you're bad at the game, like you just want to sack and like you don't want to think and you don't want to be able to make mistakes and you can't like hardly ever misplay with Lightsworn. So that's kind of like what some of the takeaways are with it. The other thing is like the real life example. So if you want to like cut off this video, that's fine. But this is a real life example that I kind of wanted to use to illustrate the point, which was, and this is in a prior video too, but um, there was an NCAA playoff game, and I can't remember who the teams were, but it was I think MIT or something or Stanford or some like nerd ass school versus like a really good state school, and they ended up winning. The nerd school beat like the really good school, and they kind of explained what their strategy was, and their strategy in the basketball game was to incorporate as much variance as possible. So what they did is they basically intentionally slow played and ran the shot clock at every single possession, because that basically meant that there were fewer possessions in the game, which meant the game were more random. So if we look at it kind of on two extremes, let's say that there were two possessions in a basketball game. That basketball game is going to be almost entirely luck based. If there were, let's say you had to play for like a month straight and there were like 20,000 possessions, the better team's like always going to win. Like it, given that large of a sample, like they're just like eventually, they might lose a day or two here or there, but like eventually variance is going to be overcome by just pure skill. And given that large of a sample, they're going to win. So the nerd team, I think it was Stanford, tried to reduce the amount of possessions as much as possible so that variance played a much larger part in their expected win rate, and they ended up basically having a huge upset. And it goes the same like with Warrior or RGT. Anything that's trying to close out the game quickly is going to like statistically and mathematically incorporate more variance. You're just seeing less cards. Like if a Chaos Turbo mirror goes 17 turns versus a CT Warrior game that goes like 4 turns, there's just more variance in the Warrior CT matchup. It's just a fact. So that's it for tonight. Thanks for watching. I'm out.